So here we've got principal types of radiation emitted by radionuclides, radioactive atoms or nuclei. So the first one we're looking at is alpha radiation. And you can see an equation here. And it's where uranium is changed because it gives off a helium nuclei. So we have our uranium, element number 92 with 92 protons, 238. You can see the picture here, that's where we start. A particle comes out, and that's an alpha particle. It's a helium nuclei. So we put here, the uranium splits into our helium nuclei and something else. And here we see it's thorium. And that's just the one that it does, because this bottom number here has to add up to something to give this number. So 2 plus something is 92. So that has to be 90 there. And what does, I'll just move that over a little bit. So we've got 90. If we look on the periodic table, the element number 90 is thorium, TH, and it's down the bottom, just next to protactinium and uranium. You'll see it down the very bottom there. If you didn't know what 90 was, that's where you look on the periodic table. The top numbers also have to add up. So here we've got 4. It has to add up to something to give us 238. So the other top number there is 234. Now the bottom row is the equivalent. So you've got 92 protons on this side. Think of the arrow as like a seesaw pivot. On the other side we've got 90 plus 2. The top row is the same. We've got 238 nuclear particles, has to equal 234 plus 4 nuclear particles. So that's our equation. U, 92, 238, undergoes alpha particle decay. And this one has to be 90, the top one has to be 234. And then we look on the periodic table and we see 90 is thorium. So uranium breaks down into thorium plus an alpha particle. And that happens, and it happens enough, you'll lose the equivalent of half your initial mass of uranium, and that'll be the half-life as it converts into thorium. If you look at the diagram, you can see that happening there. Here's the thorium, it's the daughter, the produced nucleus, and here's our alpha particle. So that changes into a different element, transmutation. So that's our nuclear reaction that's producing alpha particles. The reaction is the source of most of the helium on Earth. Liquid helium is used to cool MRIs, so we're getting this use for this helium produced. Make sure you don't call alpha particles a radioactive particle. The uranium is radioactive. The alpha particle is produced as a side effect of that, and it goes off. It's just a helium nucleus. It's not radioactive, okay? So have beta particles produced. So here you can see our parent nucleus is carbon-14. It produces a beta particle, which is a negative particle. So you can see we've got carbon-14, which is just number 6 on the periodic table, carbon, and it's number 14 is our radioactive carbon number. It produces two things. Now we know, and you'll be told, or you'll have a hint of what it's producing. We know it produces a beta particle. Now we don't draw it like that. That's a symbol for beta particle. It's actually drawn as a small e. And it has no protons or neutrons. And its charge is -1. Now, this side we have 6, this side we have -1. We need to add something more to this side to get 6. So we have to add 7. 7 plus -1 equals this 6 value. The same with the top. 14 gives 14 plus 0, so it's 14. If you look on the periodic table, number 7 is nitrogen, so it's producing nitrogen. And you can see the equation down here. Okay, now electrons emitted from the nucleus. Where did the electron come from? We know that nucleus don't have electrons, so what happens? This number here is number of protons. Here we've got 7, here we've got 6. So a proton changed into a neutron. So we went from, the other way around. A neutron changed into a proton to give us this 7, an extra proton. That's the number of protons in the atom. So that extra proton was also accompanied by our beta particle. So beta radiation happens when a neutron turns into a proton and produces energy in the form of an electron. And that electron is ejected from the nucleus. The opposite of that is a positron. It's the antiparticle. If you think of matter and antimatter, it's the particle that has the same charge as an electron, but it's opposite. It's positively charged. And there are some isotopes that do produce positrons, positive electrons. And you could come up, and we'll do that on Friday. We'll have a look at one of the equations to produce positrons. Okay, the other one, positrons are used for PET scanning, and it's very funny, haha. Is our PET on our scanner? We're going to look at that shortly. Gamma rays and X-rays are formed. They're photons, packets of energy. Think of them as wave properties, and protons, small property of a wave. But they have much greater energy than normal light. X-rays come from the electrons surrounding the nucleus. The gamma rays come from the nucleus itself. Remember, X-rays produced by breaking radiation. No particles are emitted during gamma radiation. Okay, so it's often emitted during or as part of, or it's simultaneous to do alpha and beta decay. So we've got our gamma rays, and the X-rays are produced by electrons. Gamma rays have a lot of energy. A source of gamma rays is cobalt. Cobalt on the periodic table is 27, and the radioactive isotope is 60. These gamma rays, very powerful, as we've seen, high penetration. And you'd need 10 centimeters of iron or lead or dense metal, and concrete, up to 30 centimeters of concrete. So the gamma rays, sources of gamma rays can be very dangerous when they're inside the body. Gamma rays can penetrate way into the body, and we'll have a look at penetrating ability in a couple of slides. Here we've got some examples, and you can look through this, the types of ionizing radiation, neutrons, X-rays, gamma rays, beta rays and alpha rays. alpha particles, sorry, and beta particles. You can look at that, and that's part of the notes that you're giving us. And here's our penetrating ability. So we see alpha rays are stopped by the skin, and that was the one we saw was stopped by paper. Beta rays will go through skin, but is typically stopped by shields of aluminium. X-rays will go through, but are absorbed by bone. The soft X-rays will get some soft tissue, and CAT scans are used. They can also give you view of soft tissue in medical X-raying. But X-rays will penetrate up to lead, so lead aprons are often used to protect from X-ray exposure. Gamma rays go through a lot. You need quite a thick layer of lead, as we've seen, or concrete. Neutrons, we won't be looking at much this topic, so they'll penetrate way into the concrete.